So the first thing I want to mention is that I threw this on here as a last minute. Is we're going to I'll briefly review how you can remotely access your scope, especially with the way the world we're living in right now, and a lot of us are working from home. Having the ability to remotely access your scope is important. So I'll just quickly talk about the ways to do that. And then we're going to talk about a very brief user interface overview. If you've never used the scope or it's a little bit different than scopes you've used in the past, we're going to talk about that. And then talk about just some basic signal optimization. How do you get the signal you want on the screen, and how do you set up the scope to get the best view of that signal and the best accuracy of that signal? And then we'll talk about working with buses, but we'll talk about adding buses, defining them, decoding them, and even doing some triggering and that type of thing. We can do that. And then finally, we'll add some RF to the mix. And this is really some of the very unique features of the 5 and 6 series scopes that I think can really be beneficial, for helping you get a better view of everything going on in your system. And then I'll follow that up with taking that the next step further and some more advanced and multi-channel RF possibilities with a couple little demos that might at least help put your thinking cap on and how you might be able to apply that moving forward. So with that, let's take a look at the remote operation of your scope. As you may know, the 5 and 6 series scopes can be operated with both an embedded non-Windows operating system. It's actually an embedded Linux operating system. On the 5 series scope, it's if you don't have a drive in the bottom of it, it boots in this non-Windows operation. If you do have, the Windows drive, you put that in there and it boots Windows. Okay. On the one change that we made to the 6B, which is a scope that I'm using, is that both the operating systems, whether it's the embedded closed Linux system or Windows, they are both on a removable drive. And that can really help to ease the concerns when you have a scope that you bring into a closed area and you want to bring back out again. With the Linux, the Linux version, say the 5 series, that can be problematic sometimes. Whereas the 6B, having both those drives available, you can remove the drive, leave it in the closed area, have another drive you can pop in the scope outside of the closed area. But for those non-Windows based instruments running that operating system, we have this feature called eScope, which basically just says that you connect up the scope to your network. It could be a private network, could be a peer-to-peer connection, and you simply connect to the scope using a web browser. And in the web browser, the screen that you see is exactly the same screen you see on the scope, and it drives exactly the same way. Very quick and easy. If you have the Windows drive in the instrument, you can use any of the remote desktop type applications that Windows supports. We recommend using like a VNC program like Tight VNC. In fact, the help system within the scope has got instructions on how to set up Tight VNC, on the instrument and on your PC to be able to have remote access to it. And then we also have a third option. We've got an offline program called Tekscope, and it basically is the same scope user interface, but literally running on your PC as an application on your PC. You can use that to do offline analysis of data that was collected by you or by your colleagues. It also supports connections to multiple scopes. It doesn't give you the live operating experience like the prior two things do, but it does allow you to combine waveforms from multiple scopes. So if you had two 8-channel scopes, you could have 16 waveforms, all together on your Tekscope on your desktop. We're going to be using Tight VNC for the demos that we do today. That's how I'm connecting up to the scope. Okay, so the user interface. You can use touch, you can use the mouse, you can use the front panel front panel knobs like I'm showing over here. Some nice things that they did with the front panel here is that the little colored outlines around the buttons are all color coded. So if I added channel 2 comes up in a different color, that same color will show up around the knob. So it's very easy to see at a glance what channel those knobs are assigned to at that point. Okay. On the interface, you see these little icons around the perimeter. We call them badges. So like here's the badge for channel 1. A single tap on that badge, either a single click with the mouse or a single tap with your finger, will bring up the most common adjustment. So for the channel 1 is most commonly changing the vertical scale, right? How many volts per division. double tapping on that badge will bring up the full set of options and adjustments that are available. So kind of like the full menu for channel 1 to give you more control over the vertical settings, the coupling, bandwidth, things like that. Of course, now for the iPhone generation, it is a multi-touch screen. You can touch, drag, pinch, zoom, things like that on the multi-touch screen. And you could also do a touch and hold or a right click. These are for shortcuts, maybe quickly change like a trigger mode or an acquisition mode or a display setting. So that's available on most applications on the display. And also I want to make sure that we go ahead and check the firmware of the instrument. And the reason for that is this is a relatively new and evolving platform, this 4, 5, and 6 series scopes. And we're releasing new updates to the firmware on a cadence of about 3 to 4 times a year. And so, those updates, include things like bug fixes and things like that, of course, but also will include, new features, sometimes and many times new features that you don't have to pay for, just enhancements to the scope that you have, but then also potentially new options as well. So we'll talk about how to go ahead and do that. So let's switch over and do a bit of a live demo to look at a couple of these things real quick to the scope here. So I'm just using a VNC application here to bring the scope up here. And I'm controlling it right from my PC. I may reach back over my shoulder and control some things with knobs just to be more efficient here, but we can see from the badge that I'm clipping. So if I go and I can change my vertical setting right here. I can also go ahead and change my trigger by clicking and dragging on my little trigger level right here. So now I'm just triggering on the rising edge of that signal. And let me just go set that up here and go take a look at this signal here. So a couple of nice little things. Again, single tap brings up the most common settings. Double tap brings up the full menu. All these menus are draggable. You can touch them and drag them and move them around. They're all kind of semi-transparent, so they don't really hide things behind you. And nothing's really more than just like a tap or two away, because I can do my probe setup. I can do all these settings right from this one menu here. Okay, and all of these badges work the same way by being able to bring these kinds of things up. Okay. I mentioned taking a look and checking your firmware. You'd find that under Help and About, and the firmware is listed right here. In fact, we literally just posted a new version of firmware yesterday, and I haven't had a chance to update my scope yet. so I got to listen to my own advice. We're at 1.32 now. And the really easy way to find this is just tech.com. The easiest way to find the firmware for your instrument is on any page on tech.com. You go over here on the right-hand side, and you see this button that says download. You click on that and type the model number of your instrument in, like an MSO 58, and select download type as software and hit search. And once that pops up here, you can filter that by just firmware over here, and then sort by the newest to oldest. And here you can see the most recent version of firmware. Here's for the 5 series. For non-Windows, the 5 series for Windows, you click on that, download the file, and the instructions are all right there. So that's how you go ahead and check the firmware and make sure you get to the latest version for yourself. All right, so let's move on here to some more interesting things here. Let's take a look at optimizing the signal to get the most accurate view of your signal. One thing I always mention, because it's something that everybody forgets about, is passive probe compensation. In the old days, we had the probes with the little compensation adjustment. You connect up to the compensation signal on the scope, and you adjust that. The probes that we have now can essentially compensate themselves, but you got to initiate it. So the passive probes that come with the scope, when you plug them in and you double tap on the channel badge and go to the probe setup, it'll recognize the probe and the serial number of the probe. And all you have to do is connect it up to the compensation signal and hit this compensate probe, and it will do the automatic compensation for you. The nice thing about it is that each channel has memory behind it to remember the compensation settings for that particular probe. And this is really important, especially for the passive probes that we supply with the scope. If it's a 1 gigahertz or higher scope, these are 1 gig passive probes, which is kind of unique. So if you take the time to compensate each probe on each channel once, that's the only time you ever have to do it. You never have to worry about it again. So I just encourage you to go ahead and do that. The other thing I wanted to mention, because it's something I see people oftentimes forget about, is the difference between position and offset on the vertical settings. And I'm going to show you what I mean by that. Position is literally just the position of the waveform on the screen, where offset allows you to add or subtract a DC offset on a signal to allow you to zoom in on a particular portion of your waveform, like a small little wiggle on top of a power supply rail, for example. So I'll show you that real quick. This is also where you might want to take into account what bandwidth you actually want to use to measure that signal. You don't want to use any more bandwidth than you really need, because all that does is just add noise. And I also wanted to show you a little bit about what we mean by a stacked or overlaid display. So let's go and play with all of these things here. All right, so the passive probe compensation, we can see that my probe is already compensated here, so I'm not going to go ahead and do that. The vertical position and offset, this signal here, I can, you can see it's my ground is right here. I can actually adjust the position like this and maybe increase its size. I can do this with the knobs as well. But let's add another signal here to channel 2. So I added channel 2, and I can see it says it's clipping, so it means it's somewhere above or below the screen here. So let's bring that back on screen. So I can see I've got this signal here on channel 2. What I should mention is the circuit that I'm looking at is a bus controlled synthesizer. So it's a little synthesizer chip that's got a SPI bus to tell it to tune to different frequencies. So we're going to go use that as we build through this the story of how to use the scope. So if I wanted to optimize things like triggering, if I want to trigger, say, on the negative edge, I can do that. One thing I'll mention is that when you make adjustments to either horizontal or vertical, the horizontal and vertical adjustments are made around these little icons here. Like this is showing ground in both these cases, right? For channel 1, channel 2. And then the horizontal is going to adjust around this. You'll notice if I change my horizontal scale, okay, that point, that triggered point, that negative edge is staying in the same place. If I move the position, either using the position knob on the front panel or clicking and dragging that position, that becomes the new point that I'm going to scale around as I change my horizontal scale on the scope. So the same thing holds true on the vertical. We could see that this signal here is centered up around 1.1 volts or so. But if I wanted to, I could see I've got a small little variation on that. But if I go and adjust my vertical, make that signal bigger, and I pull the offset down, I'm going to get to the point where I don't have enough offset range, or excuse me, position range to see that signal. So this is where offset can help. So if I go into the channel and let's go and set this offset to be at about that voltage, about that 1.1 volts. Okay. Now the pivot point, if you will, when I change my scale is going to be offset by that 1.1 volts. So now I can make the scope a lot more sensitive and see that variation of that signal. Now this is actually the tune voltage for the VCO inside the PLL. And there's a bunch of noise and crap on this board that I have here, so we can see it's pretty noisy. So again, to optimize this, let me just throw the 20 megahertz bandwidth filter on there. So now I can actually see that change in that signal. So what I've got here is just a little trigger signal that's coming off my microcontroller. And what that's doing is initiating a change in the frequency of the synthesizer. And we can actually see that change in the tune voltage happening here. Play with that offset a little bit. So just kind of optimize that signal there just a little bit more. And now you may have noticed that these two waveforms are on their own set of scales, right? You can see I've got one set scale here, one set scale here. The default for this scope is that whenever you add a channel, that channel gets added to its own, we call it a slice. And what that allows you to do is to optimize that waveform to go, nearly full scale for that slice, and that takes the best advantage of the analog to digital converter. Because in the old days, all we had was this overlay mode where waveforms are just on top of each other. And oftentimes what you would do is maybe make the waveforms all smaller and adjust the position of them so that they wouldn't all be overlaid on top of each other. And the problem with that is that you don't get best use of the resolution of the converter. So we default to this stacked mode of operation. But you can always switch back and forth, and I'm going to show you a way of doing that selectively here in a little bit. Okay, so there's some basic operations of the scope just to optimize the signal, look at the signal the way that you want to go see it. So let's talk about working with some digital signals. We have this logic probe called a TLP 058. And we call it a logic probe, but I don't really like the name of it because it's not just for digital signals. What this probe is if you have one of these, you can plug it into any of the channels, and basically that channel, instead of now being an analog input, is essentially 8 digital inputs, but really not just digital. What I mean by that is that the threshold can be adjusted individually on a line-by-line basis. So you can see I've got thresholds for all these 8 bits, if you will. It can be adjusted between plus and minus 40 volts, like I'm showing here. So this logic probe could be used to look at not only logic signals and digital signals, but it could also be used to look at mode pins, discrete signals in an aircraft. It could be looking at power supply states or something like that. So for example, if you had a complex trigger condition you wanted to trigger on, hey, when this power supply comes up and this one goes up and then this pin cycles low, I want to trigger when that happens. Right? Rather than burning 3 scope channels just to set up your trigger, you can do that with 3 of the inputs on this logic probe, even though, so it's again beyond going just logic application. So it just extends some of the capability beyond just doing logic capability. When you set up buses on the scope, the buses can be configured using either analog or digital inputs. You can use your analog probes, you can use any of the digital probes, digital lines from the digital probes, or any combination of all of those to set up that bus. So you can add an unlimited number of buses. Really, it's just a matter of how many you've got on your board and how many you can probe at the same time. You can just keep adding them. Unlike some of the scopes of the past where you could have 1 or 2 or maybe 3 or 4 buses defined at the most. We don't really give you a limit on that. Buses can then be decoded. You can actually look at address lines and data, things like that. And depending on the bus, other various states like start and stop bits and that type of thing. And then you could also use the search engines to search for particular occurrences within that bus and also be able to trigger on particular aspects of what's going on with that. So we're going to go take a look at that right now. Switch back over here to the scope. I have one of those logic probes plugged into channel 3. So I'll just turn channel 3 on and I can see some digital activity here. Okay. Like, I'm going to zoom in here a little bit more again just to kind of see that activity a little bit clearer. So the lines we're interested in are actually D0, D1, D2. That's actually my SPI bus. So if I double tap on channel 3, I'm going to turn off the bits I don't want to see right now. Okay, and just these guys here are going to be the bits that make up my bus. So then I just go over to the add bus button down here along the bottom. So we touch on that. And in my case, I'm using a SPI bus. And the clock input for the SPI bus is on channel 3, D0. And pull this up here to make it easier to see. The slave select is channel 3, D1. Whoops, channel 3 and D1. And then the data input is channel 3, D2. And now I can actually see the decode of that bus happening right here. Very simple. Oftentimes when if we go back out to look at the larger activity here, you can't really read what's going on in the bus activity. So this is where a bus decode table can really help. So if you come up here to where it says results table, you click on that. There's a number of different tables we can bring up, like a measurement table, a search table. But if we add the bus decode table and I add that, now I can actually see what's going on that bus. And what's nice about this is that you can use this to even navigate your way through what's going on. So for example, I'm going to pause the scope here for a moment so it's not jumping around on me here. And if I just touch on this table, you notice the little A that shows up right here. That little A right there tells me that I can take the multi-purpose A knob on the front panel and rotate it around to walk my way through the table. In fact, if I zoom in a little bit more, just rotating my zoom control on the front panel. Now, if I rotate my A knob, I can literally walk through every one of these states, and it's zooming in at every one of those lines on my table. So I've got a timestamp of when that event occurred and what the addresses are, or the data that's occurring on that bus at that location in time. Let's say, for example, instead of triggering on that falling edge, I want to trigger whenever the data is 00 hex. I can go into the trigger panel and set the trigger type, instead of being edge, set the trigger type to bus. And then the defaults it knows what buses are available. If I had more than one bus, they'd show up here. It's defaulting to slave select active, but let's change that to data. You can tell it how many data words you want it to, maybe you want to have trigger on a particular combination of data words, maybe like 2 or 3 words or something like that, or just one. And you can go ahead and adjust these values. The A and the B knobs can be used to adjust the value and which digit we're dealing with. So if I change these both to 0, now we can actually see my trigger location right down here is triggering right after that data 0 happens. So one nice thing about this this interface too is it's all pretty flexible. If you don't want this table up top, you can drag from the front top border and move it over, put it somewhere else, and maybe drag the border of it and change things a little bit. So you can really make the interface look the way you want it to look. So now let's take a look at kind of going beyond your grandfather's mixed signal scope and start adding some of the RF to the mixture. I mentioned that what we're looking at here is this SPI bus controlled synthesizer chip, and we're tuning frequency. We can see that in the tune voltage, but let's look at what the RF activity is doing. And this is what's unique about the scope platform, is that behind every channel of the scope is an RF digital down converter, very similar to what's inside of a signal analyzer. Okay, so our input signal comes in, from the probes and things like that out here into the input signal conditioning, which is amplification, filtering, attenuation, into the 12-bit analog to digital converter. The data from that converter going along the top path here is your normal processing path for the time domain waveforms that you see. But then also that same data is made available down to this digital down converter. Okay, that digital down converter does essentially RF baseband acquisition. What we're storing, if you're familiar with the RF terminology, is baseband IQ or baseband quadrature data over time. And that gets put into memory along with the time domain data. So everything is time correlated. That data is also available to the trigger system. So we can actually trigger on aspects of the signal coming out of this digital down converter, which is really powerful. What this means now is that the spectrum measurements that we're going to make are no longer tied to the time domain acquisition system like it is with an FFT. And I'm sure you've used FFTs on a scope before, that if you want to get, optimize your view for the FFT, you're not necessarily going to have the optimized view for the time domain view of that waveform, and vice versa, because resolution in the frequency domain is equal to the time duration in the time domain, and it kind of gets ugly. By having this separate digital down converter path, the acquisition system knows that it can take a look at what you asked for things like center frequency, span, and resolution bandwidth to control that acquisition. And then we'll take a look at the normal time domain acquisition to control what's going on in the time domain. Everything's time correlated, but they're controlled separately by the settings that make it, for that particular domain. So this allows you now to also view spectral activity versus time. So let's go take a look at this. And this is where you can really tie all your systems together. So right now I've got the RF signal coming in on channel 4. So if I double tap on channel 4, I'm going to change that to 50 ohm termination. I'm going to turn that display on. And let's increase the size of that a little bit. This is actually a 2.4 gigahertz signal. If I double tap again on channel 4, you'll see this badge down here, this drawer that we might call it, called Spectrum View. Now, Spectrum View is a free feature, comes along with the scope, but if you've got old firmware in your scope that's more than about a year old, you won't see this. So there's another example of why you want to have your firmware kind of updated, because updated firmware gave you this feature that we're going to show you here. So let's turn on Spectrum View, turn that open. I'll just turn it on with a normal spectrum trace. Now I think I'm going to rearrange these a little bit, maybe put the spectrum up there. So now I have the spectrum badge down here. Let me turn the zoom off here as well. Okay, so if I double tap on the spectrum badge, I'm going to change the center frequency to 2.4 gig. All right, well, let's knock the span down to about 50 megahertz or so. All right, so now I see the spectral activity here. Okay, let's actually go pause this for a moment and take a look at what we have. So remember, the frequency is changing, each time I get one of these bus activities, right? So on the time domain display for the RF signal, I see this little colored bar right here. We call that spectrum time. So that's where this spectrum measurement is actually being made. If I take that spectrum bar, I can move it by using the pan control as part of the horizontal, knob set, or I can literally click and drag on it. Now I can literally see how the RF signal is changing over time. So if I with it positioned right here, if we kind of look up here, I can see that this is kind of the lowest frequency that we're tuning to. And we see if I'm going to keep advancing forward, and you're going to see as I advance forward in time, that next place we tune to, we can see the spectral content of that signal now move. Okay, centered right around that 2.4 gig, right in the center. If I keep moving over in time, okay, we can see I keep moving this over, then I tune to the next stage. So because I've got seamless baseband IQ data here, I can use that to essentially, in effect, slide an FFT anywhere within this acquisition to see what that RF activity is doing. And this is what I mean by being able to look at the choreography of your analog, digital, and RF signals all at the same time. Let's talk a bit about some of the advanced and multi-channel RF capability that we've got here as well. There is an option that can be added to the scope that adds what is known as the RF versus time traces, right? The frequency domain traces that I just showed you, normal, min hold, max hold, average, that's all standard. You get that for free. The RF versus time traces really kind of starts to get into the realm of basic vector signal analysis. Allows you to look at the magnitude of the RF signal versus time. Really great for looking at like radar pulses and things like that, or some other types of modulation in the amplitude domain, as well as frequency and phase deviation over time. Okay, you can almost think of these as an AM, FM, and PM demod views of the signal. So let's actually go take a quick look at that first, and then we'll come back and look at a couple of other things. So let's go run this here again. Let me set my trigger back up to edge on channel 1, so things are a bit more stable here. So if I go to my spectrum view on channel 4 again, we see I've got RF versus time traces. So in this case, the amplitude we can see is not really changing much over time, but we know the frequency is changing. So let's add the frequency versus time plot. Okay. And so now I can actually see channel 4 frequency versus time. This is kind of like that FM demod, like I said, FM demod view of this signal. So, so this is really looking at the frequency deviation in the vertical axis here with respect to the center frequency. Okay, and you can see, well, this waveform really should and does match up with the tune voltage that's going into the VCO up here on channel 2. In fact, you can really make some arrangements of the user interface here to make it easier. So for example, if I touch and drag that channel 4 badge, I can actually drag it over and stick it right up next to channel 2. So now I can really compare those two very easily. Okay. Even better than that, I can selectively stack those two traces on top of each other. So if I just literally drag and put that badge right on top of channel 2, now those two traces are stacked on top of each other. And I can literally compare those two traces right on top of each other. So in this case, I'm looking at the tune voltage to the VCO and the frequency deviation versus time of the RF output of that PLL. So that I could look to see if I have any non-linearities, any clipping, any dropouts, any problems in the linearity and the operation of that VCO within this synthesizer that we're looking at here. I mean, these are tricky things to make, tricky measurements to make, kind of with any other tool, if you could even do it. So some really powerful capability here. Now, I also mentioned you can actually trigger on these RF versus time traces as well. So for example, if I bring up the trigger and say I want to trigger on channel 4 frequency versus time, this is literally triggering on the demodulated frequency variation of the RF signal. Okay, so if I set that trigger up, so I'm doing a falling edge trigger on that. So if I adjust that level down, we can actually see, I'm triggering right on that edge right here. Okay, if I change the slope of this, okay, let's go change the slope to rising edge. Okay, and we'll adjust my threshold up here. Maybe I'll trigger on one of these rising edges up here. Okay, so it's triggering on the rising edge. Sometimes it's occurring during this one hop here. Sometimes it's occurring at a different hop. But literally being able to trigger on these frequency domain characteristics, and that can be done both on the magnitude versus time as well as the frequency versus time plot. So really get a really nice comprehensive view of the analog, digital, and RF capability or signals that are going on in your system. Let's take a look at being able to do multi-channel RF. Remember, I mentioned that this digital down converter exists on every channel. Okay, so this one example I'm going to do here, and then I'll let you look at that drawing while I'm actually making configuration changes on my scope up here. Is we have I've got a signal generator that's generating an LFM pulse. Basically, there's an LFM chirp coming out of my SIGGEN. Centered at a gigahertz, about a 200 megahertz wide chirp. Okay, and that's going into channel 1 of the scope. Okay, and there's also a copy of that is going into a mixer, and then I've got a 4 gigahertz LO feeding that mixer. So I'm going to then upconvert that signal centered at 1 gig, and I'm going to upconvert it through that mixer. So let's actually go take a look. And I'm going to just save yourself from watching me hit a bunch of buttons. I'm going to just load up a setup file here for you so you can see what's going on here. So here I've got, there's my chirp coming into channel 1. I have the RF magnitude versus time trace turned on here. So this is essentially the RF magnitude of that pulse. I'm actually triggering on that. And this is the frequency deviation versus time of that chirp. Obviously, when the pulse is not there, right, I just have a bunch of noise, right, and that makes sense. And then when the pulse is on, I can actually see the frequency deviation of that. All right. Again, the spectrum time right here. If I move that around in time, we can actually see the spectral content of that signal at different locations within that pulse. Okay, so this is just looking at channel 1. All right, now channel 2, we turn channel 2 on. This is the output of the mixer. So let's turn on the spectrum view for channel 2. Okay, so right now, both channel 1 and channel 2 are both centered at 1 gigahertz. Okay, so this is my input signal about -7 dBm, -7.2. But coming out of the mixer at 1 gigahertz, I'm about -46. So I've got about 40 dB of isolation, if you will, from my IF input to the RF output. Pretty typical for a passive diode ring double balance mixer. Okay, but since the LO that I'm putting in is at 4 gig, right, I'm going to upconvert this signal centered at 1 gig up to 5. So if we go into the spectrum view or spectrum tab, I have the option now of unlocking the center frequency across the channels. So if I unlock them, now I can separately change the center frequency on a different channel. So if I set this now to 5 gigahertz, okay, now I'm looking at the spectral content of this centered at 5 gig. And we can see that's sitting, I don't know if you can read that, but it says about -14.2. So I've got about 7 dB of conversion loss, okay, between input to output. And again, if I move the spectrum time, we can see that those two move in lockstep because we're doing a simple up conversion. All right. In fact, if we go back to spectrum view on channel 2, I turn on the frequency versus time plot for that one, and we can see that mirrors what we're doing on channel 1 because it's just a perfect up conversion. In fact, we can lay those two guys on top of each other, and you can't even tell the difference between them. Right? They're sitting right on top of each other. But I don't have any filtering after that mixer. So in addition to having the IF plus LO, I also have the difference. So I also have an image at 3 gig. So, because remember my input is at 1 gig, my LO is at 4. So I'm going to have an image down at 3 gigahertz as well. So let's put that up there. So now that image is going to be inverted. We can actually see that in the frequency versus time. We're moving in the opposite direction in the chirp. And obviously, if I move the spectrum times back and forth, you can see the spectral content moving in opposite directions because I've inverted that signal because I'm looking at the other side of the LO. Okay, so it just gives you one quick view of one of the things you can do with having this RF digital down converter available on every channel and being able to set the same or a different center frequency on every channel. And we could even separate the spectrum time moving on different channels as well. The other thing I should have mentioned earlier, and I'll mention it now, is that all of the normal scope-based measurements can be applied to those RF versus time traces. So for example, this trace right here is showing my RF magnitude versus time. I can go to my measure and say, I want to measure maybe the pulse width and maybe the rise time and the fall time of that RF pulse. Okay, so I'm doing basic vector signal analysis on the scope. Okay, to build, so I got a 40 microsecond wide pulse, 568 nanosecond rise time, 600 nanosecond fall time. Okay, so lots of really powerful capability in terms of being able to look at, modulated pulsed RF signals and then look at that in multiple domains on multiple channels. Okay, so one final example is another kind of a channel-to-channel application, a CW pulse at 3.9 gig going into one channel, and then into the second channel, the same pulse, but going through a step phase modulator. Okay, so we can actually look at channel-to-channel phase capability. Okay, so here's that 3.85 gigahertz CW pulse on channel 1, also on channel 2. Channel 1 phase versus time, you can't really tell. Well, actually, if I go in here and I configure this view and turn the grid off here, let's see, turn the grid off, might be easier to see. So you actually see that the phase is essentially constant. And what I've done is I set up channel 1's phase versus time to be a master phase reference, so that the phase of all the other channels are going to be made with respect to channel 1. Okay, so we can actually see now here on channel 2, here's that same pulse. I don't have the spectrum of that one turned on right now, but then I can look at the phase of channel 2 with respect to channel 1. In fact, if I lay those on top of each other, it might be easier to see that as well. You can actually see the phase difference between those two channels. So if you're doing any kind of electronically steered arrays and you're looking at modulator characteristics and things like that, you'd be able to look at that kind of thing here. Of course, if you're doing any kind of phase modulation like Barker or polyphase codes and the pulses, you can look at those things as well. And you still have some of the old traditional and old school ways of looking at things as well. If I go to plot here, one of the things I can add is an XY plot. And if I XY channel 1 and channel 2 to each other, you kind of get the familiar Lissajous pattern, of looking at the phase difference between those two signals. Okay, so lots of visibility and be able to look at signals in different ways. This is purely just a two RF signals with a trigger pulse that I'm looking at here, but certainly we could add other signals here as well.